Shall we start? Yeah? Okay. Hi. Hi all. I'm
Sorry.
I'm Mark Wielaert. I work for Red Hat. Among other things, I'm responsible for valgrind in Fedora, RHEL, and developer toolkit. Developer toolkit is new versions of developer tools for RHEL, because RHEL is stable. So sometimes you want newer versions of tools on it. So if anything is wrong with that, just bug me. Or actually take a subscription to RHEL or use Fedora for free and bug me. So this talk came from a discussion we had on the glibc list. Started with the sanitizer developers who had some problems because glibc also does memory protection by fortification of C library functions, and then the sanitizers would either not see it or have to intercept different functions. And it is interesting that you now have different memory protectors that somewhat try to do the same thing on different levels. So glibc does fortification of C library functions on a very low level, and that's mainly what this talk will be about. Then the sanitizers, they compile in checks, and they are more dynamic. The fortification is mostly statically checking. And then of course you have valgrind and memcheck who do whole program address space tracking. Fortification. Most distros now build with this enabled. So you just define fortify source to 2. You can also define it to 1, but that's not that interesting. And when you define that macro, it causes some lightweight checks. Interestingly enough, there isn't that much documentation about it. This is kind of it. Which was surprising, so I hope by this talk I explain a bit more what it really does and why you actually should do it, and partly why it is somewhat vague is because it really is just defining the fortify source macro, and then basically anything you compile can do something. So it's what we see, it isn't actually just these memory operations, but in glibc it does a couple of other checks also. So fortification is basically one somewhat complicated but very cool compiler trick. There's a function built in object size that gives you the size of an object given a pointer. And then you have some C processor tricks which then take the output of built-in object size and do the checks. So that's really nice and a nice magic function. Also built-in object size is actually it has documentation. Yes, here it is. But it is kind of I found it hard to understand really what it does. So it returns a constant number of bytes from pointer to the end of the object pointer points to, if known as compile time. And then you can give it a type which is defined as 0, 1, 2, or 3. And that changes the behavior a bit. The thing is that it has to be known at compile time. If it isn't known at compile time, then the function will return either 0 or -1. In the documentation it's always called -1, but it is size max, of course, because size t is a unsigned. So depending on type, you can say that's nice. I don't know the number, or well, pretend it's as big as can be represented. It basically only works if you optimize, because then the compiler really can see the object behind the pointer. If you the glibc sources actually check if fortified source is defined, they error out if you don't use optimization. But in fact, you don't have to. It will just return 0 or -1. So to simplify this a bit, if you are using this yourself, and I think you should, because if you provide a C library, then I think it's really nice to provide fortified. There are so many things you can do wrong, well, let's just try this out first. So just set the type to 1, and then it will return size max if it doesn't know how big the object that is being pointed to is, and otherwise it will return the largest remaining size sub-object the pointer points to. So this example let's just you have p which just points there. Int is 4 bytes long. It points at the start of b, so built-in object size of p is 4. The same for q, which points just inside this arrow. The remaining size of the arrow is 9. And this is nice. It doesn't really know the object size, but it can give you, at least if you give it 1, the largest sub-object size that is still available. So that's 9 in this case. With the type, you can do other tricks. Some of them I don't actually know when they are useful. So as a kind of homework exercise, you can try type 0, 2, 3. And 0 is kind of interesting. There it gives the remaining type of the outer object that's in there. That's sometimes useful. So R points to P or Q, and Q points 1 after the first, and the remaining structure is 24. Is there padding involved? Yeah, probably there's padding between here. So now it doesn't give the minimum but the maximum. I've seen this used in glibc if you have a read function, for example, that you give a buffer and they think, they probably know the whole structure layout and they want to fill it completely. The others give the minimum of the sub-object and the read the here what we always will use is you get the maximum of the subtypes that are being pointed to. So here is one example that's really nice and small and immediately shows why this is so useful and why I think everybody should add it. You have a checked version of get current working directory. You give it a buffer and you claim the size of the buffer. What glibc will do is it has this function and says, I want to know what the buffer length really is, and if the size given by the user is bigger than the buffer really points to, then I fail, otherwise I give you the current working directory. So how it works is, I actually cleaned this up a bit because glibc header files are interesting to read, but basically it defines this new function. It redirects the original get working directory to an alias. It directs the checked version to another alias called warn, which has an extra attribute, a warning attribute that the compiler can see, and then the magic. Your get working current working directory, it asks the size of the buffer. If it doesn't know the buffer, then okay, we just call the current working directory. If we do know the size and if we do know the buffer size and we know the size at compile time, it's actually a constant. Let's see, why does this? Oh yeah. If it is not good. So if it is a constant, we are here, then we check the constant against the compiler constant, and we call the function with the warning. If everything is a constant, then this is defined as an inline function in the header file. So just the warning function gets called, and you get a warning at compile time, which is really nice. Otherwise, if we do know the buffer size, but the size given by the user isn't a constant, then we call the checking function. Nobody would write this code, but I actually have made this mistake myself. And this is why I think fortified functions are a really good idea, because, well, compilers should work with stupid people like me. Here I thought I should give the maximum path to get working directory. And of course, that should have been the size, which is 16. The funny thing is it just works, of course, because I have a short name, so my home directory name is short, and it's perfect. If we run it under valgrind, valgrind will see, wait a minute. If you would run it somewhere else, then the system call would override some unaddressable bytes, and it even tells you that is right after where you malloced it, which is line 9. Probably there was something before that. So this is really great, but it could actually be better. If we compile this with fortify source, then the compiler already gives a warning. The warning message is somewhat confusing if you don't know which tricks are being used, which is kind of a bummer. I don't know if we could make the compiler smarter. Nice thing about this is that it doesn't need any smarts, it just needs a header file which is smart. But this is actually better than having to run it on a valgrind. If you ignore this warning, it's just a warning and who compiles with W error, you should, you can actually run it. And ta-da! The buffer overflow is detected. The program is immediately terminated because here glibc kind of deduced something bad will happen. You will overwrite some memory that you're not supposed to. The only bad thing about it is this is where did I call what? So you would like to then, at least that is what I always do, is run it under valgrind. We get the same thing and that stack trace that aborts. Which isn't so nice. So why do we have this problem? So the problems we see with it are it's not as good and expressive warnings, but on the other hand, it is much earlier. It only works when the compiler can statically deduce buffer bounds, which actually is surprisingly often. But it blinds the other memory protectors because the actual bad usage isn't done anymore. So the other memory protectors don't see it, even if they have much more information that they could give you about the address that is being misused. On the other hand, it might actually flag something that valgrind or memcheck would miss, because the object knows the object size. And as we saw in that first example, if you have a large structure, memcheck might think, yeah, well, there's addressable memory. I don't mind if you write over that. So that's nice. But on the other hand, and that was the complaints from the sanitizer people is it might obscure tracking of memory usage because the standard functions don't get called anymore. To be honest, I first thought, oh, that's a big problem, but valgrind is mostly immune to that because it has this whole program view of the world. But other sanitizers don't, or you should rebuild your whole world with the sanitizers, including glibc. And first, I'm not sure glibc can be compiled, and then you wouldn't want to do that in production because it does really slow down your program, and worse, people have been doing it in production. But the sanitizers come with their own libraries which do various things during error reporting, and people quickly found out, hey, I can misuse those to overwrite files, or then you have your sanitizers work against you and introduce new security issues. But it would be really nice to have the good without the bad. And at least for valgrind we can, happily. What should we do? First, we should make valgrind aware of what the address was. So instead of just aborting, what checkval kind of does, we provided the address that caused the problem. So that's basically a simple change in checkval. We say, okay, something bad happened and it was there. And then we either overwrite checkval or we annotate checkval to make valgrind aware of the issue. First, we make the memory non-accessible, or tell valgrind we don't think that memory should be accessible, even if memcheck thinks it is. And then we ask it, is that memory accessible? Well, no. And then we fail like normal. And amazingly, that just works. And we even just get the original that address was allocated at that line. So this is really, really nice. Except as soon as I suggested this, glibc developers are conservative. Let's call it that way. So that bloats the code. You have to pass an argument, you have to calculate the argument. Every instruction is one too many. So yeah, they kind of have a point. They really want this to be always on. So anything that might get people to turn it off, they don't want it. Then they said, well, you didn't really do your homework, because it's not always an exact address. We use it for everything. Oh, right. So for example, select takes file descriptor sets, which are really a byte set, a bit set of which, so if you try to put a file descriptor bigger than file descriptor maximum in there, they generate a check fail, which is correct because they would calculate a bit outside the file descriptor set, but right. And they are kind of right that you don't always know the exact address, or you have to calculate it because there could be multiple buffers. Anyway, and this is actually a good point. Valgrind could give even better messages hints. That is true because here you see that, well, it's an address of bytes found during client check request. Yeah, that's we could do better, and sometimes we do. So we already have some overrides for memcheck, and actually I believe it's only those 4 that we override, and then we do, for example, overlap checking on the buffers. And so yes, we could, but to be honest, most of them are really as simple as get current working directory, so there is not that much more than we can do. Wow, I'm going really fast. Yeah, okay. Yeah, I had one other slide that's not here, but so I'm slowing down and I'll try to do this one slide in 20 minutes. Sorry. So the issues is I haven't done most of the work. There are 75 check functions in glibc, and about 50 of them are like get current working directory. So instead of doing this presentation, I could have actually done that. The other 25 are somewhat more tricky. So if you have the SN printf family of checks, that actually sets a flag that gets checked by the normal printf code. So you can't really rewrite them completely as an override. And there is a problem that GCC gets smarter. Darn compiler. So GCC now has built-ins for this set of functions, and what glibc does is just, if fortify source is on, then we just alias string encopy to built-in string encopy check, and GCC inlines it all, and there isn't a function left anymore. It only has check fill that does get called. So in that case, we can override check fill and produce at least a better backtrace, but without an address. And that's interesting because all these built-ins really work on a specific address that you would override that is bad. I really want to ask them to please make an exception and call something like check failed address with an address to make us happier. I actually had one conclusions. The conclusions were if you have a C library, you maintain a C library, and it takes buffers and sizes separately, please think about adding fortification. It really is it isn't that nice, but it isn't that much work, and it really saves lives. Well, lots of programmer frustration. And if you do, please add something like hints to client requests to valgrind. The glibc people obviously don't like this generates code. It does generate code, but it generates a slightly complicated no-op. So it shouldn't really be that hard. And this really is in your slow path if something goes bad. So if you don't do that, then write a failure that is just specific about what the failure was. And finally, yeah, maybe I should work out these functions maybe in the hackathon at the end, and then go back to the glibc GC people and say, look, I have to write so much code, can you just have different failure functions to call so that we can overwrite them nicer. Okay, you haven't put up any sign, so I guess I still have 50 minutes, yes. Okay, well, let's see if people have any questions. Yes.
I think I'll add 2 comments. So first of all, this technology is quite old, about 12 years old in glibc, so it's mature and you can safely use it. 12 years. And I think that, well, the check file is on AirPod, so it's not a problem to put some code there.
Yes.
I have no problems. I mean, taking my glibc head on, I have no
Oh, okay.
taking off.
Good. Well, this talk was a success for me at least.
So you have my act for an address argument if you need.
Okay, no, we probably have to introduce different check because currently there are only 2, I believe, check fill and check stack overflow fail, and there are some places where check fill is called where it doesn't involve an address, so probably we should have 2, but maybe you can discuss that. Yeah. Okay, good. What was your question?
You are mentioning there are 75 overrides.
Yeah.
It seems quite small compared to the whole glibc. Does it mean that it's not possible to provide more overrides or no one?
No. There are 75, depending on precisely how you count, functions that have been fortified in glibc. My estimate is 50 of those are like the get current working directory, where you just have the buffer and the size, and you do some checks on the buffer length and the size.
And so the rest of the functions in glibc is not able to be fortified, or they don't have to be done?
I don't know if they went to the max or not. I believe these are the most. I don't know.
Okay.
Yes.
What about playing side-by-side? Does valgrind have the ability to play nice with those in any circumstances?
So the Clang.
Clang provides similar features as the fortified source code for detecting incidents.
repeat the question. Yes, Clang provides some of the same features. I think you're calling about the sanitizers that are shared between GC and LLVM. So those work differently. Here, most of the checks are done in a way that can be checked at compile time. And the sanitizers at runtime checks. So yes, you could, but I think what the sanitizers come with helper libraries that you link against, and what we could maybe do with valgrind is have our own implementation of those helper libraries. I know Julian actually implemented for Upsen support to have valgrind itself be Upsen checked. Yeah. So it was so easy that Julian doesn't even remember. The memory checkers are not as simple as the undefined behavior sanity analyzer. But I think it could be done. But we have to see. I think it wouldn't be that hard because LLVM and GC share them. So there must at least be some documentation on them. So maybe it can be done, yes. Yes?
Valgrind observes, check more precise, observes the malloc calls, but at the end, Valgrind knows it has been allocated, it doesn't know the time which is behind this malloc memory.
No.
Valgrind also can read the debugging form, which describes types, that's used for XP SG check. What do you think about an idea to modify the compiler to tell to tools like Valgrind that this malloc call is allocating this type so that the type could be remembered by tools like memcheck and then could be used to do better diagnostics?
Yeah, so I did think about it. The question is, can we annotate malloc or memory allocation functions with the type and maybe use the debug info to which describes which pointers point to which variables have types. I couldn't make that work because the IR works too low level. You don't know why you have a pointer or why you do a.
But of course, we would have to change the compiler so that it would generate some calls to a helper function to say the malloc calls we will do or that we have just done, by the way, it is this kind of type. And then
the IR GCC, right?
No. In valgrind,
no, it's not possible to
No, but then you can it gets very hard to keep associating a type. What you could maybe do is GCC now has support for MPX, the memory protection from Intel processors, and what those do is they have an extra set of registers that describe the bounds of pointers. So maybe we could reuse something like that.
Runtime, and more speaking about changing the compiler so that it says, here I see a call to malloc, and I know that I will assign the result to a pointer of that type, So at this place, I inform tools like valgrind or other tools that this pointer, no, here is the type.
So you're proposing to actually the compiler to generate a piece of code which tells
Tools like valgrind or other tools that, and so then you track the type, and then when you dereference, then you know what is being dereferenced.
Yeah, so my conceptual problem, I can't really think about it because the types are not what we work on. We work on instruction streams, and I don't know.
I'm confused why you're confused.
Okay.
So in GCC you're compiling something and then
Yeah.
there's a call to malum, and you maybe know what object, the type of the object you're allocating there is. So GCC generates a piece of code alongside the malum call which tells valgrind what the type is.
Yeah. But
Sorry?
Yeah, specific compiler option to say help tools to track types.
Yeah, but this instrumentation is not valgrind, it's on the GCC
Yes.
side.
okay, yeah, okay. So yes, you are right. So why am I confused on the valgrind side? Because I don't understand on the GC side how you would then pass on that type, because yeah.
For this instrumentation, it's not separate segment like, well, the debug information is stored or something.
Yes.
And, well, when you load binary, you load some additional segments, so load use some tools like valgrind. And well, in a way, you load more information, you can add this information to it or use it, so annotate just. How you annotate, well, is line of source code, you can annotate this type information.
I don't think the compiler is the right approach, because depending on your language, if you want to do ASM, you do not have types. The type is just a point of view from your language. But what you could do is doing some static analysis to detect memory patterns, memory access patterns, and then you can detect inconsistencies there.
Yeah. So here is ESG checking functions. That is each some limits for up to be quickly.
It depends how you do that.
For sure, you can never work all the time, but I would imagine that the most of the time when GCC is compiling C++, it pretty much knows the types of objects that are being allocated.
Yeah.
You know, if you're calling malloc from an constructor for a class, then you know.
So maybe it is more like what I said for the MPX extensions, because there what they did was output instructions that set up bounds for every pointer based on the object sizes, and then you have it in the instruction stream, and that would be easier for valgrind to see. And I also think abusing or using the sanitizer libraries might be an easier way. Okay. Yeah? That we